So I want to talk today about Bayesian inference. I think in this crowd, at least some of you would like to be doing that. I'm going to talk about sort of trends that have been happening over the last 4 or 5 years in deep Bayesian inference, scalable Bayesian inference, whatever you want to call it. Some things that are not working so well with that we really run into limits in my lab. And I will talk about some ideas that we've been working on. This is new work, so I am excited to get feedback from people and sort of show you what we've been up to. All right, so let me start by telling you some things you already know. And introduce some notation just so we're on the same page. So for purposes of what I'm going to do today, I'm going to assume that the X are the data. So some high dimensional data set has some distribution. We probably can't write this down. We probably don't know a lot about it. I'm going to assume today are some latent variables. They don't have to be real, but this might be a useful model of the world. That these are some lower dimensional things. I'll assume for the talk today that this is a real vector, but we can talk about that kind of data later. There's some prior down here, and I'm going to assume that there's some generative model that we'd like to write down and maybe like to do something with. And usually what that would mean is we want to figure out what the posterior is. So you give me some data, and I tell you about these latent variables. So this is a very, very common setup. And the point is, and any statistician will make this point to you first, if we care about uncertainty, we want the posterior. That is, if we have data up here, especially neural data, which are incredibly noisy, then giving you a point estimate of this thing is probably not a very honest thing to do. We would like to talk about how uncertain we are, and so we have a full probability distribution. The other thing that you know, if you are interested in kind of in this field, is that most of Bayesian statistics is about avoiding calculating integrals, really, really high dimensional integrals, which are really hard to approximate. The gold standard, if you care about uncertainty quantification, is still markup chain Monte Carlo. I will tell you my personal experience, if you're using general purpose methods like STAN or something else like that, if you have more than about 10,000 data points, you're sort of boned. Like, there's not much you can do about it. It's going to take you a couple of weeks to run this model, but if you really care about confidence intervals, or I should say credible intervals, it's going to take you a couple of weeks, a couple of days to a couple of weeks. So this is the problem setup. This is things that everybody knows are hard. All right, so I want to talk a little bit about variational Bayesian inference. So this is a different way to approach these things. This is now fairly common, comes out of ideas in the late 90s. And the idea simply goes like this. We're going to take our probability distribution P, and we're going to swap it for something else Q. Q is going to be parameterized by some set of parameters phi. These days, it's often a neural network, but it can just be some giant set. And we're going to minimize the Kullback-Leibler divergence between our approximate posterior and the true posterior, which we really don't know. So this is the setup. This has been around for a long time. Sorry, I'm blowing through this. And one of the benefits of this is you get what's called amortized inference. That is, you train your model. Maybe that takes you a while, a couple of hours, a couple of days. But then you can calculate the posterior in order one time. So this is the setup. We're going to do inference as optimization. So just to show you, we use this kind of technique a lot in my lab. We specifically use variational autoencoders. This actually worked by Jack, who's in the room. Here we're showing birdsong syllables. So we compress these spectrograms into some latent representation. We reconstruct them. This is that KL minimization to first order. And you get these latent spaces. So these would be the Z's. And as you move through this latent space, the morphology of these syllables changes. And you can cluster these syllables in latent space. And they look very nice and clustery. So that's all cool. All right, so what's wrong with this? What's wrong with this is that VAEs tend to produce blurry reconstructions. This is actually the machine learning thing that's wrong with it. It's not the one I'm concerned with today. But this is the reason VAEs got surpassed by GANs and normalizing flows and diffusion models and all sorts of other great things. So now this is pretty low-grade technology for machine learning. The other thing is, though, there's no guarantee that if you train this model twice, you're going to get the same latent space. I have some work on this with my graduate student, Miles Martinez. It's not as bad as you might think, but there is no guarantee. So if you want to compare results that you get from one of these latent models across data sets or across labs, that presents a problem. You essentially have to retrain the model all over again with new data, and you may not get exactly the thing that you got before. But the main thing that we know is wrong with this, and we've known this from a long time, this is from Chris Bishop's book, is that there are two forms of this KL minimization. So this is what we call the forward KL. So our true posterior is on the left, and our approximate posterior is on the right, and KL is not a metric, so this is not symmetric between these two. So forward KL is what's called mode covering. So our Q, so if our P is this bimodal Gaussian distribution, so this is one mode and this is the other, our Q is going to cover both of those. So we'll get one Gaussian that covers both. But if you actually minimize the reverse KL divergence, which is what we do in variational inference, then you get this mode, or you get this one, but you don't get both. And what that means is that your uncertainty estimate is way, way too small. This is a known problem, and to be honest, in practice, I have never seen anyone treat uncertainty estimates from variational inference as anything other than wishful thinking. For the most part, if you're running a standard vanilla VAE, I know there are people in this room who are working on better versions of this, but for a standard VAE, we look at the uncertainties, but we don't think they mean a whole lot. There's work on addressing this that goes back to Tamara Broderick and other people, but it's not really made its way into the mainstream. All right, so I want to talk about a couple more ideas just to catch you up to sort of where things are in the field. There was this idea of normalizing flows, which was really cool. So the idea is you start with something that you can sample from easily, like a Gaussian, and you, through a series of steps, you feed this through a whole set of functions. They're pretty simple functions, and the idea is that you turn your simple distribution into something complicated. Now, one of the things about normalizing flows is we're not going to be able to write down a probability density. This is what's called an implicit model. It's the same idea as with GANs. But if I have a distribution here and I feed it through a deterministic function, then I get a distribution here. The downside is, if you remember your sort of calculus, you know that you need the log determinant of the Jacobian to do this. So you need a log determinant Jacobian that you can write down exactly. You need to be able to compute it quickly. And this is great. This will give you really, really nice samples. So you sample from a Gaussian and you get a nice sample from your data distribution here. It has some downsides. One is that I've not told you anything about inference. If you want to go backward, you need all those functions to be invertible. So that's a pretty small class. And now, in practice, you need a couple hundred of these to get really good samples. So it's a beautiful idea. The other thing is that since these functions are kind of injections, you need this data dimensionality to be the same as this data dimensionality. So there's no compression here. So these primarily are generative models. They're models for producing really nice looking images or time series or other sets of things, but they've not really been used much for doing inference. The other more recent thing, which probably a lot of you have heard about, this is now way state-of-the-art for image generation, is this comes from an idea from a paper that is in machine learning years now ancient, the Sol-Dixstein paper. But then Yang Song and Stefan Irwin's lab at Stanford really figured out how to scale these things really well. So the idea is the following. I'm going to start with an image, and I'm going to add noise to it. And that noise is governed by some stochastic differential equations. So there's this drift term, which is deterministic, and there's some noise term. And the idea is the following. You add noise, and you learn to reverse it. So a little bit of theory. There's actually a reverse stochastic differential equation which takes you from noise back to images. It has this particular form, and what I want to draw your attention to is this thing called the score function. So this is the time-dependent density of the data, and this is the gradient of its log. That's going to be the score function, and if you knew this thing, you could exactly reverse this process. So what diffusion models do is they take one step at a time, and they figure out how to reverse that, and one step at a time, and figure out how to reverse that, and you build up a representation of the score function. So that is the idea. These things are incredibly successful, right? This is the core technology behind DALL-E and all of these other image generation methods, though they have a lot more bells and whistles. All right, so I would say I started this thing out saying we care about doing Bayesian inference, and we want to learn something about maybe distributions underlying our data. And so I was promised posteriors, and I was cheated. Because the truth is that inference has kind of fallen off the map in generative modeling. Generative modeling now is about generating data, and you can have Bayesian models are generative, but not all generative models are Bayesian. So the inference piece of this that I care a lot about as a scientist is not really part of the discussion. When we have inference, a certain quantification is really bad, so maybe it's worse than not having anything at all. Our latent spaces are not uniquely defined, so we don't actually have the latent representation. We have one, but another one may be equally as good, and we don't know if we're going to draw the same scientific conclusions from that. And our best current models are really trained to race relationships in data. All right, so we've been working on a set of things. So this is the wonder bread portion of my talk, but I'm happy to take criticism of this. Everything I'm going to tell you about today is the work of a really amazing MD PhD student in my lab. Duke MD PhD students are kind of next level. So this is all work by Daniela that we're writing up now. I'm going to talk about an approach that will give you uniquely defined latent spaces. We're going to get correct posteriors up to a controllable error. We're going to get competitive generative ability, and we may get, I don't know, I can't say this with a straight face. Speaking of things that are loaded terms, I don't know. This is entirely up for debate. All right, so if you only pay attention to one thing today, this is the slide. This is the one slide, this is the core idea. So I'm going to give you 3 views of that same diffusion process I talked about earlier. So the first one, and this gets started a little bit slowly, this is the diffusion model. So we start with the 2 moons data set, and we're going to put noise into it, and it's going to mix, and at the end you get a nice Gaussian here, and everything is mixed together. So this is one view of diffusion models. Many of you know there is another view of this, which is where we just look at the density of the data, and this density satisfies the Fokker-Planck equation. And so the density of the data is also going to slowly blend together, and eventually we're going to end up with a nice Gaussian. So this, if you want to think of it, is just the coarse-grained version of what's happening here. So this has got a stochastic differential equation that says what happens to the particles, and the density here is what happens to them in aggregate. There is another version of this that I'm going to talk about today, which is a view of this which is melting. And this actually satisfies the same Fokker-Planck equation, but is, I think you can see, something with very, very different properties at the end of this. And so I'm going to talk about the relationship between these things. So this is the whole idea today, is we're going to do this instead of this. All right, I'm going to do the same thing, but with math. So we're going to deal with this diffusion model. Again, there's a drift term, and this thing is sort of the square root of the covariance matrix at any given time. There is this time reverse model that goes from here back this way. And there is some Fokker-Planck equation that does this. If you're not getting this, don't worry, this is not super important. What is just important is that there is a link between these 2 things. You need to know the score function here, and that probability density satisfies this partial differential equation. But in Song's original paper in 2020, well, not the original one, I guess it was a couple in 2021, they actually point out that there is another version of the probability density that satisfies this Fokker-Planck equation. And that's an ordinary differential equation. There's no noise here anymore. This looks a lot like this reverse equation with a couple of halves thrown in, but this ordinary differential equation that goes from here to here actually satisfies the same Fokker-Planck equation, and the key ingredient, again, is the same score function. The other important thing to keep in mind is it doesn't matter if you solve this thing or this thing, they're the same score function. So if I can train a diffusion model, I can actually also do one of these probability flow with ease. All right, so why do we want to use this sort of thing? Well, one interesting thing is that for a given data set, and a given stochastic differential equation, this guy is unique. There is one and only one solution to that equation, and it gives you this. The mapping is now deterministic. So there's no noise in this. I can start up here, and I can tell you exactly where things go down here. This is stable, so as you can see here, we're just shading this to show you context, but we're preserving local structure and nearest neighbors here. So things may spread out a little bit, but when they do, that's under controlled things that we can prove theorems about. The other thing is there are 2 components that I told you I needed to do this. We need to do numerical integration to follow this ordinary differential equation down, which has very well understood theory and controllable error. Basically, you just take smaller and smaller steps as you go on. And you need to approximate the score function. And this is a little harder, but basically I'll say if you look at TensorBoard and you sort of get your noise at the end, you can estimate how bad you are, and that badness can also be mitigated by integrating with smaller and smaller steps. All right, so what I've not told you yet is what diffusion we should use. So there's a standard one in score models. In fact, in the Song paper, they actually offer several, and the one I'm going to be concerned with today is the so-called variance preserving model. So the idea is basically this. If you remember diffusion, you drop a density of something, that drop kind of moves out forever. And so what we're going to do is rescale our coordinates, or in their case, what they talk about is reducing the noise over time, so we end up with a Gaussian that fits within bounds. Those 2 perspectives, one is that we're going to change our noise over time, the other is we're going to rescale our coordinates, are equivalent to each other. So I'm going to talk about coordinate rescaling today. All right. The other thing that's important is that if I start with data that are a plane in a high dimensional space and I add noise with diffusion, they blow up in every dimension. So again, I'm going to end up with a latent space that now has really, really high rank. So that might be a problem. We might want to deal with that. And we want a process that sort of preserves local dimensionality. Maybe even reduces dimensionality, but I'll start with one and then do the other. All right. So there's a really, really simple choice to this, and that is we're going to choose a solution to that Fokker-Planck equation that we can write down really easily, which is I'm just going to take every data point and I'm going to do a kernel density estimate, or I'm going to melt it. I'm going to convolve it with a Gaussian kernel, so every data point becomes a Gaussian that spreads out in time. So this is just like you're smoothing your data with a bigger and bigger smoothing kernel. And that is a solution to a certain Fokker-Planck equation, and that certain equation is has zero drift, and it has a diffusion constant, which is the time derivative of that spread. This is a really simple Fokker-Planck equation. We're doing kind of the easiest version of this, and we're going to do some coordinate rescaling. This is just a technical condition, but if you satisfy some technical conditions, then you get a Gaussian as the solution. So that's all I'm going to care about, is that I end up at a Gaussian at the end of the day. All right, this gives our version of this probability flow ODE. I'm just putting in blue here. Again, this is the thing we don't know and that we have to estimate. Everything else here we're gonna choose. So if I can estimate this score function, again, by fitting a diffusion model, not my model, but a diffusion model, then I'm fine. All right, but I need to tell you what C and A are. In other words, I need to tell you how fast we're doing the smoothing and what the rescaling is that we're doing. So I need to digress a little bit. So this is a figure from this paper by Gao out of Surrey Games Group. And they introduced this dimensionality measure, which is nice and has some good properties that we want to use. So this is called the participation ratio. So our data have covariance sigma, and I'm going to have the trace of sigma squared over the trace of sigma squared. If your eyes were closed, you will need to look at that equation. The properties are really simple. When sigma's rank 1, the participation ratio is 1. When sigma is proportional to the identity, in d dimensions, you get d. If you have any ellipsoid shapes, that's going to reduce the participation ratio. And so this gives you a model of dimension that depends only on second order statistics, as invariant to linear transforms and all these other things. So this is the measure that we're going to work with. All right. So as a simplicity, I'm going to work in principal component space of the data distribution. In fact, these covariance kernels are going to have the same principal components as the data. So everything here is going to be diagonal. This is now my participation ratio. And you can convince yourself with a little algebra that if I want it to be invariant, I need to satisfy this condition. And the simplest solution to this is actually just that you blow everything up exponentially. So my axes change with some constant exponential rate. And I used to be a physicist, and I think that this is inflation. So we're just inflating away all the information in our data. And you can choose the rescaling so that you get a Gaussian asymptotically. And that Gaussian, you can choose what it is. All right, this is the movie portion of the talk. So for those of you who've been asleep, movies are better than science, and so we're going to show you movies. So this is a couple of examples of what this looks like, and they're a little slow to get started. Where did it get started? There we go. And slowly we're going to fill these things in. And you can see that at the end of the day, you get a nice Gaussian. We're preserving local structure. This works in 3 dimensions. Oh, anyway, it works. The other important thing is we can do the reverse. So if we start with Gaussians, we can use these to generate data. And we can go backward to the original data sets. These are colored slightly differently just to show you that we're picking out sort of different things. But again, this is orderly. These were the points that were sort of high in the hollow notice distance, and they're the points that end up far from each other. And you can get even fairly complicated data sets to generate with this method. It shouldn't be surprising, given that I told you this is just an ordinary differential equation that we're dealing with. Let me show you the trickier thing. So I would like to reduce dimensionality. I would like to get a latent space that actually is a compressed representation of what's going on. I'm going to remind you of this equation that we had. I actually want something that contracts here, and it turns out that a solution for this is, okay, if g is 0, this is what I had before. And now what I'm going to do is I'm going to change the expansion rate of different dimensions differently. So I'm going to have some dimensions that expand really quickly, and the rest of them are going to expand really slowly. And then what happens asymptotically is I can reduce the dimensionality to some k features where this is max. So you can imagine I'm putting a bunch of 1s in here and some negative numbers, and all the dimensions that have 1s are the ones that stick around. You can do an isotropic rescaling, and then you get some lower dimensional Gaussian out at the end. All right, so just to show you that this works, and then we just collapse down to the dimension. This is not just a linear projection. I got worried about this like a week ago. This is not just PCA. We're actually smoothing things out in a way that preserves information. The S-curve is also, this is a little hard to tell from the angle, but is really basically a 2-dimensional plane. And you can go backward, actually. This is the thing. And when you go backward, you're going to see that, of course, we're pretty good. We lose some information here, right? There's no free lunch. And I told you I compressed most of the information out of this. And so when I get back, I'm clearly losing something. So what we care about and what would be hard to do in practice, and we're still working on, is figuring out how far to push this. We have to choose this number. So this is one of the hidden secrets, is we're trying to figure out how to do this on data sets. This does not tune itself. All right, but I will tell you that on real data, so this is CFAR 10, and we're going to reduce it to 2% of its dimensionality. So this is 62 dimensions. This is just to show you that the round trip looks pretty good. We can start, say, here, and we come back to here. So our round trip performance is really good, even though we're compressing most of the information out. You can see that this is not white noise. This is there's some covariance structure here. But we can also do pure generation. So these are generated from CFAR with 2% of the data dimensionality. So we get pretty good generative performance, again, because we're training this on a diffusion model, which we know how to do. In fact, it turns out to be a cute fact that you can use pre-trained diffusion models to do the same thing. So if you have a diffusion model that you've downloaded that works on a data set of the right dimensionality as yours, you can actually, the trick is that what you actually do is you take your diffusion model, which is used to adding noise in isotropically, and then you run time at different rates in different dimensions. And that actually allows you to use our schedule with a diffusion model that's pre-trained. So I asked Daniela to do this, and you can see here, this is without any dimension reduction, but you can see here that we get really, really good round trip, and we get really, really good pure generation. All right, the important thing, and this is the real stats geek thing I started talking about, is for, if we specify all these things that I've said, and these are choices, this mapping is unique. And what that means is that since we have controllable error, I can do things like preserve local structure. So that means that I can take something like an uncertainty around X. My prior on X is a certain Gaussian or a certain ball, or my prior on Z is a certain Gaussian or a certain ball, and I just do bidirectional sampling. So what's going to happen is I'm going to melt these. These are my uncertainty regions, and you can see that they're very, very well behaved under either one of these. And you indeed do get correctly calibrated, almost exact estimates of coverage for these intervals. So for the handful of people in the audience who are really into this, I hope this hits. So we were really excited about it, and this is what we wanted, because now what happens is, if we start with a particular confidence set around a piece of data, then we can actually be confident that when we melt down and we're taking these samples, we can get a good estimate of coverage for what's left. This is true even when we reduce dimension. It's going to look a little funkier. By the way, I'm zooming in here to keep things visible, because otherwise they shrink very far down. And they look weird, but they're still well behaved. And the same thing is going to be true on the other side as we zoom back out. If we started with some ball down here, and those balls are very, very thin in this dimension, they're going to blow up, and they're going to have some funky shapes, but they're not crazy. Like, if you look at those coordinate-wise, you're still going to be well calibrated. So I want to end with one last thought on this. UMAP is in the news again. Many of you have been following this on Twitter, and UMAP is great except when it isn't. UMAP is great except when you believe it. It's a great way of looking at your data, though I think it's appreciated now. It has a lot of tunable parameters. There's a lot of fiddling that goes on under the hood. You have to pick a random seed. And in fact, when you do that, you can end up with something that takes a nice, well-behaved Gaussian distribution and gives it all sorts of weird and cool shapes. So something we've been talking about in the last couple of weeks, and this is certainly not finished, is the idea that, in some ways what I've told you about is very uninteresting. I said you can take really complex data and you can map it to a Gaussian, and that's not very fun. Maybe you get relative relationships. But the other way to think about this is the Gaussian is whatever you choose to map here. So it's possible that you could do something like take all natural images and ask how your set of natural images embeds within that. So in the same way that I said this, we think about this, we do a lot of work on birdsong, taking the whole space of syllables across 50 or 100 songbirds and making this our global prior, and then embedding a bird's individual syllables, which will look like little blobs in here. And so this gives us a way of thinking about embedding data in some kind of, again, we have to pick this. We have to decide what our prior is about the world. But you can imagine doing this with animal pose. You can imagine doing this with, we've not worked on the time series case yet, but a similar sort of thing. If you have images from calcium imaging data, you can imagine that there's some similarities in those. And now this is kind of your model of the world, and this is what you are embedding in it. And so we're starting to think about this for some larger data sets. But I want to stop there and have time for questions. So again, this is all Daniela's work that I'm talking about. And thanks to our funding sources and the other members of the lab.